thinking about each of those points, right? Each of those points. And now under those assumptions, then we get a functor. We get those functors, H alpha G, when I restrict to this category, those points, to abelian groups. And so for every alpha, and part of the yoga of this theory, which I want to explain. By the way, this notion, as I mentioned, was suggested in the first example was given by Grant Siegel in the ICM 1970, and actually he described what we can call a stable cohomology equivariant. So equivariant right, and so but now then later on Peter May and his school, May and a bunch of things, really developed this theory fully. And one thing they observed is that under those axioms, this becomes that this is a Marquis functor. What is a Marquis functor? It's actually, this is a contravariant functor, but also we have a covariant property of basically if you have a map between two, if you have a G map between two such things, you can, it's an exercise to show that to have such a G map, then H must be conjugate to a subgroup of K. So this is kind of a surjective map, surjective G map. So this induces a pullback, right, because this is a contravariant functor, but also it implies a push forward from this of this space to this space. This is called a transfer. And actually this is valid. They've done the significant work really when you do with compact Lie groups. Everything I'm saying here can be done with compact Lie groups, which is a much more complicated picture because you have
to also simply connected or the conjugated?
No, these are finite groups.
Yeah. Okay.
Okay, so I started finite. So
for compact Lie groups, you take only closed groups or what?
Very close subgroups, yes. But these are the orbits, right? The stabilizer point is always the close stuff. The actions called. Anyway, so and then when you have this kind of covariant contravariant functor, right, you also have the pullback, and then satisfying some properties. And basically one of the main properties is so-called double coset formula. Then you call that a Marquis functor. And so he showed that this is always true under this axiom. And also conversely, I'm not going to write this down, but if you have a usual, so a cohomology theory that is graded, which is graded by the integers, satisfying all those axioms, then it can be, if the cohomology of a point is a Marquis functor, then it can be extended to a full ROG graded theory. And so, but now, then what's the dimension axiom now? So the dimension axiom under this assumption is that H alpha G of G mod H is equal to 0 if alpha is different from 0 for all H. And so of course that now here, this is, I can write something like this, E A G sub H, and where A is a Mackey functor. So if I, and the theorem is that, so basically then the fact, just in the case of no equivalent cohomology theory, is that exist unique. So given a Mackey functor A, and I'll give examples of that. Exists a unique erosion-graded theory satisfying everything else, satisfying the axiom, satisfying the dimension axiom. Right, just a single cohomology. And so examples of Mackey functor, I'm going to give you only two examples. But one is where the name comes from. If you study representation theory, you have this notion of Mackey induction, right? That you play around with induction and restriction of representations. And the so-called double coset formula. Okay, so that's someone's not right. And so examples of a Mackey functor examples of Mackey functor is one is a representation ring. Representation ring. Right, so the idea is that I sense is a functor that sends in orbit, so it's something in the category of orbits, to the representation of H. Right, and so if you have a map from this to this, basically this is a conjugate subgroup of this, then, so it's F, then that induces sort of a pullback, right? Remember that this is sort of conjugate to a subgroup of this, and by taking that with some, this is just the restriction. This is the restriction map. And then you have a push forward.
You mean lower shape?
Say again?
You mean F lower shape at the beginning? In the F admirado? The
This
primero.
one.
Pulpa? No, pulpa.
Well, because I'm saying from this to
Oh,
this.
so, yes.
And now this goes from here to here. This is the induction. And so it's restriction induction. So, and there's an example of a Mackey functor. One example, that is only given if A is any abelian group. So exists a unique way unique way to make it a Mackey functor. That basically assign G mod H goes to A. But now the difference is that this is just the identity. In this case, there will be the identity. And in this case, it will be multiplication by the index of H and K. And I am avoiding some technicalities, but that just, this is a conjugate subgroup of that, so that index here. So, all right. So basically, when we started to transfer, that you basically were adding up everything on the fibers, and so that is precisely the index, right? So the fiber of this map has a size precisely the index of this limit here. All right. So so there is one such theory. Now there comes exactly the question that was asked before yesterday. So maybe you can ask the same question now. So how do you construct those things? So one construction, and so it's a construction. The construction for the ordinary case finite groups, construction of this. The unique algebraic theory satisfying the dimension axiom, we call that ordinary. Now, for those who are familiar with the work of Bredon, right?
Here, this definition G is finite. Yeah?
Yes, but could be compactly given.
And you have to consider the quotients.
Yeah, but in that, then the definition of Marquis-Funkes is more complicated. You have to resort to some stable homotopy theory to define sort of the transfers and so on. But essentially, it's some. In spirit, a lot of those things have to do with multiplying by the Euler characteristic of I won't go there. But so this theory, if you look only at what I call the trivial directions, so the indexing, and actually the notation for this now will be simply H upper alpha G, and so X A, where A is the Marquis-Funkes. And most from now on, I'm going to be really only talking about constant Marquis-Funkes like that. So this, if alpha is an integer, in other words, that means n times the trivial representation. This was Bredon cohomology. So if you go back to the literature, there's a work of Bredon where he does this type of ordinary cohomology by doing homological algebra in the category of coefficient systems. Right, and so, but now, if this coefficient system, the Bredon language, is a Marquis-Funkes, then it uniquely extends to this theory. So sometimes I call this Bredon cohomology, although Bredon only dealt with this case. Right, so now, how do you construct the ordinary cohomology theory? Actually, I will do with Z coefficients and indicate how to do with other coefficients. There's no difference from what I've done last time. So that's the beauty of it. So let me write a theorem, and this theorem has, I think, it could have a lot of names attached to it, but I did some part of it at some point, and then Dos Santos, and then Zalconi and others. Marcelo, did you prove any version of the equivalent Dalton theorem as well? Yes, I do. You are. Sorry, but maybe it's just different. But I'm just presenting the form that's more suitable for the talk. So basically, if Z is representation of V of G, then remember that I said that Z0, this is the one point of the sphere. Remember, I defined this yesterday. Basically, you can think about 0 cycles of degree 0, or it's the same thing as Z, the free abelian group on this, topologized mod by, say, the point at infinity. This is a connected space. This is a quotient of two groups. And so that's how I introduced last time. But now this is a space with G action. The action on G, on V, induces an action here. Then this is a K Z space. In the sense that, in other words, therefore, and this is explaining this statement as well. If you write alpha is an element, remember that the representation ring, an element here, is a difference, right? We have visual representations, so it's represented as a difference of two representations. If alpha is equal to that, then when you compute h alpha g of x z, which this is the constant motif functor is here, then this can be obtained as you take the Darwin sphere, you suspend the negative part, smash with x, add a base point outside of x, and then you do base homotopies into this SV equivalent. Base equivalent. So in other words, the theory that if you take the free abelian group, the theory is for arbitrary alpha, I see as V minus W, I can represent in this form. And so, and I will not write down any of that, but I could go on and explain what is an equivariant spectrum along the same lines that I've done before, but I think it bears no relevance for what I'm going to talk later. But basically, this creates what called an equivariant spectrum, which now indexed by representations, by orthogonal representations, and it comes with a natural equivariant homotopic equivalence between this and V plus W, and so on. So it's a collection of spaces with this property, and I want to narrow down now to one particular example. The narrow down to the particular example is one of your group is say a Z mod 2, but I want my Z mod 2 to be equal to this. It's a group with a trivial element in a complex conjugation kind of, which is isomorphic to Z mod 2. In this case, my ROG is isomorphic to Z plus Z, right? When I write, so there are two non-trivial, two irreducible representations. This is Z times 1 plus Z times the sign representation. All right, so the sign, actually you can see the sign representation, for example, as I times R inside the complex numbers, and the complex conjugation gives you the sign representation here. Right, and so in this case, we can talk about, so your theory is essentially graded by two indices. How many copies of the trivial representation, how many copies of the non-trivial representation you have. But here, I would change the notation a little bit, and I'll call it, it's not my term, this was coined by Daniel Duggar, the student of Mike Hopkins. So if alpha is equal to n times 1, so if alpha is say n times 1 plus r times 1 plus s times c, so denote h alpha g of any space by, instead of, I want to do my graded version of it, but I want to denote it by h r plus s comma s g x z. So in other words, so whenever you see in this notation, whenever you see h upper n comma p g, you know that we're talking about Z mod 2Z, but the first n is the total dimension, topological dimension I'm talking about, the sum of these two. Right, just think about as a vector space, if both are positive, R plus S is the dimension of the vector space. So, and P is how many copies of this twisting you have. All right, so that's a notation. And let me give you just one example for the sake of running much. Okay. But to understand a little bit how this notation works. For example, sub-example. we're not entering in a lot of details here. So, but what is, I'd like to describe to you what is H21. And please go back to James' talk yesterday and see what H21 was back then, with a different, and then I'm going to add in the H22 over here. So first of all, I mean, if you think what H2 is, right, this is actually H of how many copies of the trigger representation I have. Well, this is H1 times the trigger representation plus 1 times psi. And if you remember well, I mean, last time I said this is, as a representation of the Galois group, this is C as a vector space. Correct? This is C as a vector space. So by definition, this is really homotopy classes of maps from this into Z0 of the one-point compactification of C, which is actually is called the projective line. It's a Riemann sphere, right? So this is really Z0 of CP1 that goes here equivariantly. And now I will not explain why, but this is really, it's a classical results of Dode and Tom and many other people. This is homotopy equivalent to CP infinity on the complex conjugation, equivariantly homotopy equivalent. And so this is topological maps. This is just the same thing as the equivalence classes. You can just pull back the universal line bundle with this of complex line bundles. Satisfying that when I take the pullback complex line bundles L, satisfying the pullback, and I take the conjugate of that, this is isomorphic to L. So this is the same thing as we call real line bundles under tensor product. Under the tensor product. Right? Just like a sort of a topological version of the real Picard group, or the Picard group of X as a real object, as an objective complex conjugation. So this is easy to see. Now this one here is more interesting. This is and I will not explain much about this. This is the equivalence classes of, we can call some sort of a quadratic line bundle. Equivalence classes of pairs. So this is a line bundle with a given trivialization. Sorry. Line bundle L with this thing. This is a class of pairs L, Q, where this is a complex line bundle. But now Q is an isomorphism of, you take the pullback of L bar, cancel with that, go to the trivial line bundle, and this is an isomorphism of real bundles. Real bundles in this sense, bundles that satisfy this isomorphism. So this one, if you take the pullback conjugate of this tensor product, you get itself, right, a natural isomorphism to that, and this is a trivialization. So you see that the 2, and the 2, 1, this 1 and this 2, they do make a difference. And without that twist, the usual way you see equivalent cohomology theories would miss this altogether, right? You do need this non-trivial direction to pick up those subtle differences. Okay, now I will end here. I was going to talk about the cohomology of a single point, which is a rather complicated. Actually, it's a fun thing, but maybe I should stick to my plan. If I have time, I'll talk about that later. But it's So an example is the cohomology of the point. Now, this actually is a bigraded ring. Where B and P is just the H and P G of the point. So the full thing now, all N's and all P's. So you know that 0, 0, it must be Z because that's what I gave before. And so the picture is like this. So I'm going to make a grid here. This is where my variable P goes. This is my variable. I want M to go here. So first M and then P. So this is the diagonal. Let's do the diagonal right here. So maybe it should be like a box. And so here it's sort of.
Sorry, Paulo.
Say again?
I am misunderstanding something. This point should be two objects, right?
I'm sorry?
There are two kinds of points for this group.
Yeah, no, this is the point. This is
Okay.
this is just G mod G.
Okay.
That's G mod G. Everything becomes a ring over there. So everything is sort of. It's an algebra. So the cohomology of this space is always an algebra over this. Okay. So now let me do like this. So this 0, 0, I get a Z at 0, 0. At 1, 1, I get. Let me write. I want to write Z star. That's just plus or minus 1. It's Z mod 2, but I want to write in this form just because it makes it. This is Z star over here. And then it's going to be Z star over here. Along the diagonal from this point on is Z star. Here at 1, I get a 0. And then at 2, again, I'll have the same thing. I'm going to have a Z. And I'll have a generator that I call tau over here, Z times 1. There's the element, the non-trivial element, so this has two elements. I will denote the minus 1 here by epsilon. Okay, I'll call that epsilon. So, and then epsilon squared generates this, epsilon, the third polygon, that goes like that. Here I have this tau, I multiply by epsilon, I get another Z star. So this is generated by one element, they call epsilon. For those who like K theory, you should think about epsilon maybe as a minus 1.
So
And epsilon squared, just a second, this symbol, minus 1, and so on and so forth, like that up here. All right, yes?
So it's two sets epsilon?
No, I'm just saying this is generated by one
No,
element.
That's fine. I mean the one to the left.
This is 0.
This is 0, and then the next one is
Oh, the next one is
okay.
Z.
C.
But I'm just saying
Generated by
this is
epsilon.
level 0, 1,
Okay.
2, 3, and then level 3 is 0 again. But here now I have tau multiplied by epsilon, I get now an element tau epsilon, etc. So basically the idea is that below the diagonal is 0, is that this first quadrant, it's just, you can think about the polynomial ring on two variables, epsilon and tau, but with the provision that 2 times epsilon is equal to 0. That's familiar to many. Now, what's interesting is that, unfortunately or fortunately, this thing has negative roots. So here is 0 at negative 1. So this is 0, negative 1. In negative 2, it is Z, negative 2. Then it's Z mod 3. Oh, sorry. It's Z mod 2, so I can write again Z star in negative 3. And then from now on, it's going to alternate between Z and Z star. So it's going to be Z here, it's going to be Z star here. And it's going down. Now, from this point on, then these are the diagonals. So here's going to be Z star all along. And every entry is a Z star. And the ring, it's not a finitely generated ring by no means. I mean, so this is. So now here, I call a generator here is generated by an element alpha. It's a cyclic movement by an element I call alpha. Here is generated by an element that I call theta. So therefore, alpha belongs to H0 minus 2, theta, well, what I call V, or 0 minus 2 up there. So it becomes V0 minus 3. But what's interesting, for example, the multiplication is that alpha times tau, is actually 2 here, not 1. And so that's a source of a lot of subtle behavior in this thing, as opposed to, there is something called an associated Borel theory, which is more familiar to everybody, that is related to the usual grand cohomology, that if you do that, you localize with respect to this element, and all this part is killed and becomes 0-2 periodic. So basically, all those lines repeat up and down. There's no negative, nothing on this side. They all flip to this side. But in general, this is a very complicated thing. Z star, Z star, Z star, and all these things up here. Okay, so now let me I could explain what the generators come and the ring structure is, but I can do that privately. What about that? If you want to know. But that shows that it's so we have, with Pedro dos Santos, we have an article where we compute this cohomology ring of all real quadrates with excruciating details. And that shows how it behaves in the signature of the quadrant and all that. It's an interesting ring structure. And should have interesting applications that we have not done. So we've done that to all real curves as well, but we never published it. Maybe we should. Okay, so now what I'm going to do is I want to, as I said before, the idea is that we have spaces, and to calculate cohomology, we send spaces into another category where you can do homological algebra or some sort of homotopy theory, right? If you go to the spectrum way, you do, homotopy class of maps in polydiagonal spaces. If you go to complexes, right, you do homotopy classes of maps from the singular complex of X to this thing that's represented by something that I call R. Is the complex concentrated in degree minus R. So this is kind of an Allenberg-MacLeod space. So what I'm going to do here, I'm going to propose a third way. Now, this is a part 2. It's now using hypercohomology, and you all had a crash course in hypercohomology yesterday with James. Right, James? So I will assume that you know hypercohomology. No, I'll say a few words to that effect, so I will be more gentle perhaps than James. So what we want, is how to represent. So now you have those groups, right? Remember that this gives you singular cohomology. So small line here. Singular cohomology, or I want to represent this in the equivariant sense. Zero by n. What kind of maps coming into here? So of course the way I'm going to do is going to be a very particular way that will basically, and the reason I'm doing this to be more transparent next lecture and in my main lecture. But I'll tell ways of constructing this that will now have a differential geometric flavor, right? So have a differential geometric flavor, but in a much more general constructions. For example, I think the work of again Marcelo. I'm very glad you're here because I always refer to you for further questions. But you have notions of this paper about some type of, it's not vibration, how you call that you can kind of cover, it's a ramified type of coverings that you can, so you can do that in a very general topological setting. I don't want to do that because my ultimate goal is to relate this with motives, and so I'm going to restrict for the moment, and so here is where the caveat comes. Remember, I said you get spaces, you find a way to send your spaces into another category, which was the complexes or whatever, and do homological algebra there. So I'll describe what this new category will be now. So in particular, if you say, hey, but you no longer have general topological spaces, don't worry, we're gonna come back. They will return. So, but I want to tell you a little bit about this, how to construct those maps, but in a very particular setting. So it's not for general spaces anymore. For that, you can go to the literature. But let me give you just some terminology. So if C is a category, called a contravariant factor any contravariant factor from this category. And here I will restrict to abelian groups, but could be anything else. Abelian groups. A free sheaf on C. Of course, the most common example, of course, is that if you have X in space, and then you can call out OX is equal to open sets in inclusions. So this is your category now. So in this particular example, if you take open sets and inclusions, in other words, the morphisms in this category are only inclusions of open sets. So in particular, if you have certain open sets that are not including each other, it's an empty set of morphisms. So open sets inclusions, then, so a pre-sheaf on C is, on this C, is the usual notion of pre-sheaf on X. Right, so if you just check the definition of pre-sheaves on X, you realize that that's the definition. That is a more general, could be any category. So, and then I'm going to tell you what means the category I want to start playing with. And let's be very restrictive. Let's be very restrictive now. And my notes disappeared. We start, I'll give a definition with a notation maybe. Let's see. And this is the set, the category of oriented, real analytic, manifolds. There are smooth manifolds that the transition functions are real analytic. That's it. And so we can also, if you have a finite group, with analytic G action. All right, so anything I'm going to be basically doing everything in this category, but in the back of your mind, you should all translate everything into this one as well. So that makes. Actually, this becomes a site with the usual topology, and I will not explain much about that. But let me just make you. So we are interested in, let's say, PSH omega, which is pre-sheaves on this category. So contravariant functors from this category to abelian groups. And so let me give an example of such thing. And then, of course, and subsequently, later, we can talk about also sheaves on this category. So there are some sheaves that has to do with satisfying some usual properties with respect to covariance of analytic manifolds. So, but let's focus on pre-sheaves. Let me give an example of such thing. An example. And that's, so let X be a space, any space. So it's a double complex. Remember, spaces for us have some restrictions that I don't need to explain much. And I'll define, I can define something like z sub x, which is something that sends manifolds to abelian groups, contravariant, as follows. So you apply this, so this is a functor that when I apply to a manifold, is going to be simply the free abelian group on the, well, I mean, this is a space, there's nothing much you can do about that. So you take the topological, so the continuous maps from your manifold X. Right? This is an example where a space generates a pre-sheaf on this category. So this, therefore, this is also functorial on X. This is really covariant on X, contravariant on M. And so this gives you a Z, is a becomes a functor for the category of topological spaces to the category of pre-sheaves, and actually can make it a sheaf. I can sheafify. So let me just do that, putting on the rug on this category. So this is a special set of objects in here. But basically, this is what fits with our previous philosophy, that we can send topological spaces to another category where I can do a beta, I'll do some homological algebra here. And using this functor, I can retrieve invariants here as well. That will come later.
Excuse me, what is Z home?
Well, this is a set.
Okay.
This is the free abelian group on a set. All right. Okay, so I've been using this notation. There's no topology there. When I use morphisms with the compact open topology, I usually put an F instead of home. So, but that's an example of doing it. So now I get it pretty close to the end. Now I will, with a little digression in geometric measure theory of sorts. And so I'd like to introduce, and I won't do that with any decent manner, there's a notion of integral currents, and then everything that has a notion of locally integral currents that I don't want to explain. And then inside of that, so on a manifold. So usually I'll denote this by I, loc, K, M, and I'll tell you what these things are. So, in fact, if your manifold M has dimension little m, then this is actually something that sits inside in the, as James described last time, this sits inside the D M minus K of M. Okay, so the topological dual of forms of dimension K. Right, so this is a particular subset of this. I'll explain in a minute. And of course, inside of those, I have, since my manifolds are analytic, I have the real analytic chains. And so since I'm much slower than I expected, and then I have a locally. So they are something that will sit over here. I call this, and I'll explain what these are. Okay, so basically after you do some of the, these things are, imagine the following, look in the open set in Rn, and look at the polyhedral chain, just a convex hull of a set of points, the polyhedron, for example. A bunch of them glued together. You can integrate differential forms on that. But if you map that into another open set under Lipschitz map, you still can integrate form of the image of the Lipschitz map. So you can pull back, and there's some measures you can do. So these things, at least locally in open set, they can be seen as limits of chains that are obtained under the image of Lipschitz maps. So they're really nice ways, domains of integration. But these ones are the ones that are the current and its boundary are supported in appropriate analytic sets of the right dimension. And so you can essentially see them as, as an element here. You can essentially think of them as locally finite, and this has a very locally finite chains. So locally finite sums of chains all corresponding to integration along real analytic subsets, submanifolds. And so when I put submanifold here, then I'll have to cut maybe some sort of countable locally, but it's, I can put this there. If I put submanifold, I have to, it's like an algebraic cycle but it's not algebraic, it's locally analytic in some sense. Oh, by the way, so from now on, things I'm discussing is work in progress, and I put first the name Bob Hart here because he's a late addition to this because he's an expert on those things, and I'm using his thesis for that, or his work. And then James, and then Pedro dos Santos. Anyone else wants to come on board, more than welcome. So now, but so now I introduce these, not very well, but an object here is a notion of support and so on. And I'll tell you a special type of those now. And part of the reason I'm doing this is to remember my question was how to construct maps from a space to the free abelian group on something, a sphere, for example. So let's keep always that question in mind. And so this is the main definition. And you see this definition in the algebraic geometric context later. Like so, and I'm really stealing the name from something else. This is not a name in the literature. A finite, say, topological correspondence. So now I'm introducing some notion of correspondences. T between analytic manifolds, let's say between say V and W that belongs to this oriented real analytic manifold, is a current T that belongs to, as this thing I said before, and now I'm using for V, the dimension of V is going to be little v, the dimension of W is going to be little w. So this is the dimension little v of the product V cross W. So it's a current in there satisfying the following properties. So the first property will be that it's closed. So the boundary of T is equal to 0. 2, the restriction pi v restricted to the support of the current is proper map. Is it proper map? particular, I can push it forward to V. Right? Because when under proper maps, you can push currents forward. And 3, the cardinality. So it's a proper and surjective, and surjective if T is not the zero current. And then the cardinality of the fibers of the projection, so phi V inverse of a point intersecting with the support of the current is finite. So, and this is a finite topological correspondence. And so actually if you still have 2 minutes instead of 1, I can tell at least what's the main punchline. Not the main punchline, but the initial premise behind introducing those things. One is that when you see the Voevodsky motivic complex, you're going to feel a sense of familiarity when you see it. But also, okay, let's give examples of that. So if F from V to W is mapped in this, so it's an analytic map in manifolds, then the graph of F belongs to, oh, by the way, let me tell that the set of those things, they form a group, right? This is a group, they form a subgroup of this, and then it's denote that by I omega V dot. Okay, sorry about that. So this is the set of all, is the group of all such correspondences. Right, so this is that thing. And so this, of course, that belongs to this omega. So another one, which is...
how do you compose correspondence in the usual way?
Oh, this is the graph. Sorry, this is the graph.
No. I mean, for the group. How do you...
No.
compose?
So here, there's no composition here. It's just addition of currents.
Okay.
It's a group under addition. It's an abelian group under addition. There's nothing else. Like right, differential forms, you have distribution. So okay, so now 2 is that suppose that you have x and y are say either real or say real or complex algebraic varieties. And suppose that gamma containing x cross, containing x cross y is something that is a subvariety, it's irreducible, that maps, who's mapped to x. This map here is a finite surjective map. And say smooth as well, because right. So now these are all algebraic geometric notions. But if you then look at the complex points with the analytic topology, now these are actually holomorphic manifolds, in particular real analytic manifolds. And then if you look at the correspondence, again with analytic topology, everything is now seen as manifolds. So this now belongs, so if the dimension of this thing here is say M, so this belongs to, well I don't need a dimension for the definition. All right. And not only that, if x and y are real varieties, then the complex points, they do have an action of the Galois group on the complex conjugation. And so this would also be preserved through a map of respecting the action of the Galois group. So I would like to end this giving just, I know I'm going to go over maybe 3 minutes, But I'd like to at least tell why I introduced those things, because well, the first, and there's more. I will address your question how to compose those correspondences. I will address that next time. Okay, but the proposition here, and that's essentially the work of Bob Hart, is that if you have V and W are analytic manifolds, and now look at this I0 of W is the group of zero currents, zero integral currents. On W. And essentially, you can think about this, actually is Z of the free abelian group of W. There's a minor difference in topology, but they have the same algebraic geometric invariant. In other words, somehow this is like the compact generated version of this or something like that. So we don't need to. It doesn't make much difference for us. So now given an element that now will say T that belong to this set of finite correspondences between V and W, the following holds. Then, okay, one, and I'll explain what this is a little bit. They slice T, pi V is the projection onto V, X exists, so this is exists for all X in V. So by definition, this is an element that belongs to, if you check the dimensions well, this belongs to the zero currents of the product. But with support on the fiber over X. So the idea is that if you see such a correspondence, it's going to be, the support would be something like this. And there is a way in geometric magic theory that if you have a current in a space and map onto another one, you can look at it. There's a way that you define a slicing of that current, and the slicing gives another current. But in general, that exists only almost everywhere on the basis. Under those conditions, the slice, it was made so that it exists for all in here. And two, the function, so let's call this maybe, let's say gamma sub t. Now I send a function from x into I0 of w. And now let's remember that with this, I want to think about this as the free abelian group on W. That sends a point x to, now I'm projecting the W direction, the current, and pushing forward the slice. It's continuous. And in the appropriate, it's continuous in the flat norm topology, whatever that means. So in other words, I give a map, continuous map from here to here. Particularly if my W is a sphere, which is an analytic manifold, that would answer, that show an example, the example I want to do of how to construct those maps. And what's nice about this is that I can integrate differential forms of those things. Okay, so we.
Thank you. We get the questions for outside. We have 10 minutes for the next talk.
My apologies for going over so long.
No, there are two announcements to make.
There are
One is
55
the
minutes.
program has changed.